given the value of x, there is a normal distribution here. Some babies' head circumference is larger and some others smaller, but actually it is like a normal distribution. So given another gestational age, say 26, the value is mean, and here another normal distribution. I draw this line negative correlate, but actually in our data here should be positive. But I just want to illustrate the concept. Okay. So we will also use residual plot to check the assumption of normal distribution. Usually we say, given the value of x, the standard deviation sigma y given x are the same for different x value. They are all the same. This is called homoscedasticity. So hard to pronounce. So this is the third assumption. And I just mentioned the linear relationship. This is the second assumption. And finally, the last one assumption is the outcomes y must be independent. So usually we collect data from different persons and they are all independent. So it would be no problem. But sometimes if you collect some data that are dependent, maybe you have to adjust or to overcome such circumstances. After 1 or 2 months, maybe 1 or 2 months, Taiwan have an election for president, right? And many companies, they will do some survey to see our population, the percentage to support the president 1 or president 2, right? Not president 1, but I mean the first choice, second choice, third choice, which will you prefer? Okay, so some company will do such a survey, and usually we only ask one person within a family. We don't ask 5 persons within the same family. Then you will have 5 data points in your sample, and these 5 persons will be regarded as correlated data because you belong to the same family. Usually your intention, your preference are the same or similar. Maybe all the 5 persons in your family support number 1. So I mean the data in such a case are correlated. They have some correlation among them. You cannot regard them as independent data. I can give you another example. If you want to estimate the death rate, mortality rate for race. So if we have 50 race, and eventually they have 10 race dying. So the death rate would be 20%, right? But why you can use the value 20% to estimate the death rate of race? There is assumption this rates should be independent. Then you can estimate a rate, a new case, a new subject, the death rate of the new subject. And sometimes if you, in your laboratory, you have a couple of rates with the same mother, so in her pregnancy, she had maybe 6 rates, maybe more rates. So in such circumstances, here is a cluster 1, cluster 2, cluster 3. If you have such cluster data, not all independent, we will say within a cluster, individuals within a cluster are more likely to be the same, with the same death rate. Within the same cluster, individuals are more likely to have the same death rate. So these 50 rates are actually not independent. Some of them are correlated, not independent. So to deal with such data, you need some advanced technique in statistics. I mean, usually it don't need to be checked, because as a researcher, as a PI, you should know if your data are independent. So it's not checked by your residual plot or something else. So we are going to check the assumptions, the first one to the third one. I will use my slides to show you. Okay. In the left-hand side, we just show an obvious outlier here, and maybe this one very close to 3-fold standard deviation, right? So maybe 2 outliers or just 1 obvious outlier. So this is the first purpose. We can use residual plot to identify any outliers. And this is the second purpose of residual plot. If the residual plot looks like this, what to say, like this shape, fan, like a fan. Okay. If it's like a fan, then it's violate the assumption of homoscedasticity. Okay. In this assumption, it means the standard deviation given any value of x should be the same. Okay. But from the residual plot, obvious some standard deviation are larger than others. Okay. And for the third assumption, no, not third. The second one, the relationship, I will give you some example. Here, identify outlier.
Here, identify outliers.
And the second purpose is to evaluate, to assess the assumption of homoscedasticity. So hard for me. To check if the variance are the same. This is the second purpose. And the third purpose of the procedure is to check is random like this, or it has some pattern. So we don't want the residual plot to have some hidden. Finally, the third, do not keep the random scatter, but instead follow a distinct trend. The trend was some hidden. So you can see in your textbook there are three purposes for a residual plot. Yeah. Right now, all the explanatory variables we have considered up to this point have been measured on a continuous scale. That means all the variables in our regression model, the explanatory variable must be continuous. However, regression analysis can be generalized to incorporate decreased our nominal explanatory variable as well. So X can be discrete or nominal explanatory variable. That means when it maybe grouping, classified into several groups, not continuous variable, it should be still work. For example, we might wonder whether one is diagnosed toxemia, the disease mentioned in our example, in your practice example. But the toxemia is a dichotomous, a binary data, right? So after introduce here the dichotomous variable, I will give you another example that involves a variable that has three labels, not only two labels. So that is an extension. And usually we take the value of 1 to indicate the presence of toxemia. Use 1 to indicate presence of toxemia, and its absence by 0. So the value only 1 and 0, 1 and 0. So what this is why it's called the indicator variable. Only two labels, 0 and 1. So it's also called dummy variable. Okay. So following our previous example, here x1 is gestational age, the same, gestational age, and x2 is birth weight. But for simplicity, we ignore the x2 variable. We just add another variable x3. Toxemia. Yeah. We add the indicator variable toxemia. We use x3 to indicate the variable. Okay, but we don't put x2 in the model just for simplicity. Okay, so this is the model we fitted, we estimate from our data set. So please note here the value of toxemia, the slope of toxemia is negative 1.4, negative. And of course you can conduct a hypothesis, and the p-value of the t-test is about 0.001. So reject the null hypothesis at the label of 0.05. And in the following slide, it wants to show you how to explain the regression line. Suppose the value is 1, x3, equals to 1, it means the mother had diagnosed as toxemia during her pregnancy, right? X3 equals 1. So you can input X3 as 1. And if the mother did not diagnose as toxemia during her pregnancy, so the value of X3 would be 0. So the same, you can input the value X3 in the model. So it results like here, y hat equals to the equation, but you replace X3 as 1 when X3 equals 1. Okay. And it turns that y hat equals the equation. The slope is the same, x1, but here is a constant, right? Minus 1.4 is a constant. So you can calculate the intercept and minus it by 1.4. Then it reduced to 0.08. Okay, so the intercept is changed. In constant, when x3 equals to 0, and you have nothing here, so the intercept is the same. So you can see there are two regression lines here. There are two regression lines. The slope of x1 are the same, but the intercept of the two models are different. So it means that there are two lines, two parallel lines, right? Two parallel lines with different intercept. Two parallel lines. And originally, if you have gestational age and head circumference, but you have no information about toxemia, if you have no information about toxemia, so it is a group of data. But once you have the information of toxemia, we use the triangle to indicate the toxemia equals to 0, and the circle indicates is equals to 1. Okay, so in this scatter plot, it distinguishes two groups of the infants, the babies, distinguished into two groups. One used the triangle and the other group used circle. So according to the circle data points, only circle data points, you will have the regression line. And according to the triangle data set that you observed, you estimate another regression line. So these are two parallel regression lines with the same slope but different intercept. Okay. So that's why we show you if you have an indicator variable in a regression line, the explanation is like that. Parallel lines observed, and you will use the distinguished regression line to distinguish the different groups of the data. Okay. So in the next step, I will show you how to deal with categorical data. If the categorical data have more than two labels, more than two groups. 20 individuals. All of them are junior high school students. And the dependent variable, Y, is the achievement in mathematics. Actually, it's a score from some exams. So this is a continuous variable with the scores in mathematical exams. Okay, this is our dependent variable, remember. And we want to explore some related variables with the dependent variable. So in the right hand side, all of these variables are potential explanatory variable. Potential explanatory variable. Okay. So we take this variable as x, and this is our y variable. Okay. Math achievement, and I would say here is the anxiety score. Anxiety, something like depressive. Okay. So if students feel anxiety in mathematics, usually they don't have good achievement in mathematics. So I would say it is a negative association between our dependent variable and the anxiety score. Okay. So let's check it. A regression line. In the first step, we just input achievement in math as dependent variable, and anxiety, total anxiety score. Okay, total. We have several other anxiety score here, but please use this one, total anxiety score, as our independent variable. So press OK. We will get a simple linear regression, right? So according to the coefficient, the table of coefficient, you can write down the regression line. Y hat equals to 33.45, not plus because it's negative, so we say minus 0.108 anxiety score, right? So it's negative, and it achieves the significant label 0.05. The p-value just 0.01. So it is a significant associated factor for achievement in mathematics. Okay. So is everyone follow me? Follow me? And we have the independent variable, say sex. And sex only have two labels here. So we still do the same thing like our textbook. Right? Now we are adding another variable, a dummy variable here. The regression line, the same. We have the x1 already, right? The x1 already, and now we want to add another indicator variable, say 6. Just press OK. So right now you can write down another regression line. Although it is not significant, we still can use this as an example to illustrate how to extend the coefficient. Okay. So please help me